Assalamualaikum warahmatullahi wabarakatuh and very good day to everyone. Alright, so welcome back to this course. In part 2, you have learned on the 4 types of hardness testing, and then we also discuss on the impact properties. How does this choppy impact leads to the DBTT phenomenon, and also some safety factors that we need to consider during application. So now in part 3, we will continue our lessons on the failure of materials. So in this part, we are focusing on the simple fracture, both in ductile and brittle hardness. Okay, let's begin with the fracture. What does it mean by fracture? Okay, fracture is basically a separation of body into two pieces or more as a result of the static load. Okay, static load. So this static load that apply to that particular body can be in the form of a tension, compression, shear, or even torsion. And this load is led to fracture. Okay, this fracture can be categorized into two, which is ductile fracture or either ductile fracture or brittle fracture. As we know that this ductile fracture have a very significant plastic deformation, whereby this brittle fracture will have little or no plastic deformation, or we can categorize it as catastrophic failure. Okay, here you can see the difference between three materials, which is very ductile, moderate ductile, and brittle. The difference between those three here, you can see here, if let's say it's a moderate ductile, we can have this cup and cone fracture, whereby this is in this region, okay, in the middle region, we call it as a fibrous crack. And at the edge of this specimen here, around 45-degree angle, is the shear crack. Same goes to the other part, which is this is 45-degree angle as the shear crack, and at the middle or at this region, this particular region, we call it as fibrous crack. Okay, so in this region. Okay, for brittle materials, you can see here the crack surface is almost, this is the crack surface, is almost perpendicular to the stress load, right? So almost perpendicular, this is the stress or this is the load, and the crack surface here is perpendicular to this stress load. Alright, so here the ductile warning before fracture means that we can see the formation, or we can see some plastic deformation, but brittle, no warning, without any notice, without any plastic deformations. Okay. Alright, let us look at the real applications of this failure. So this is pipe failure. Okay, different between ductile and also brittle failure. So here we can see it's a one piece. Okay, it's deformed one piece. It has some plastic deformation before it's failed, and it's large deformation here. Compared with brittle failure, this pipeline is like broke into many pieces, alright, small pieces. Okay, so these are some of the difference between ductile failure and also brittle failure. Alright, so let us see the mechanism of the ductile failure. So what happened during ductile failure? Okay, let us see. Okay, so there will be 5 stages, which is 1, 2, 3, 4, and 5 here. So at first stage, which is your initial loading, we apply tensile test here. Alright, at initial loading, we will create necking. So we call it as necking here, necking. And then beyond that, it start getting small voids at the center region. So here is center region of the necking area here. So we can see small voids, alright. and we continue applying the load. So what happened in the third stage? The collision of the micro voids and also the growth of the voids, whereby these voids come together and getting close and try to link each other and become a proper crack. Okay, so this is a proper crack here. Alright, and if these crack have sufficient length, so what happened at the next stage is the shearing at the surface here. The shearing at the surface will take over, which these shear forces is 45 degree to the tensile forces. Okay, so that's why at the end stage, we can see here at the edge of this specimen of this necking, we can see this is the shear crack. Okay, I did mention on the cup cone sample in previous slide, we have this shear crack whereby it is 45 degree to the tensile forces. Alright, and at the middle here, at the middle region here, we call it as fibrous crack. Okay, so at the end, during fracture, which is in stage 5, this specimen will separate into two. Okay, so these are the resulting fracture surface at this region. So we can see the particles serve as void nucleation site. Okay, if you can see in stage 2, right? And then this is in final stage, we can have a cup cone specimen. Okay, whereby this is 45 degree. Okay, we call it as shear crack, and these are the region that we call it as fibrous crack. Okay, so this is ductile failure. So how about brittle failure? Let us look. Alright, so this is brittle failure, the example of brittle failure. So basically we know that this brittle failure, the surface of the crack is perpendicular to the tensile stress. Alright, okay, this is the example of brittle failure. So this arrow is indicate point at which failure originated. It starts from this point and also this point. And for this brittle failure, the V-shaped chevron, okay, we will get this kind of V-shaped chevron in some steel, okay, V-shaped chevron. Alright, another thing about the brittle failure, this crack propagation correspond to the repeating breaking atom. Okay, repeating breaking atom. Okay, within either intergranular or transgranular. What is all about? So let us look. Okay, this is happen in the brittle fracture surface. Okay, either intergranular or intragranular. What does it mean by inter? Is between grains, and intra is within grain. Let's say this is your grain. Okay, so between grains means along the grain boundary here, the crack is start to propagate. Okay, if let's say it's intragranular, it's inter the granular, the granule or the grain itself. Okay, something like this. This is your grain. Okay, you can see this is your grain, and the crack propagate within the grains. Okay, so these are the example 304 SS stainless steel, and this is 316 stainless steel metal. And we also here have some polymer materials with propylene and also some aluminum oxide ceramic. Okay, I think this is the end of our lecture for the whole chapter, which is chapter 6, mechanical properties, metals and solid. So these are some of the summary. We already learned on the stress and strain. Okay, these are size-independent measure of load and displacement respectively. And then we also learned on the elastic behavior. The reversible behavior often shows a linear relation between stress and strain. Okay, this is stress and strain. So this is the linear, which is referring to the elastic behavior. And once it's exceed the yield strength, so we have some plastic deformation. Alright, to minimize deformation, select a material with a large elastic modulus, which is E value here. Alright, and then we also learn on the plastic behavior, which is after the yield strength. So this is the plastic deformations. So in this plastic behavior, this permanent deformation behavior occurs when the tensile, a compressive unit axial stresses, reach sigma y, which is your yield strength. This is your yield strength. And also we learn on the toughness of the material, whereby this toughness is the measurement of the energy needed to break a unit volume of material. And lastly, we also discuss on the ductility of the material. Okay, where the plastic strain at failure. Alright, with this, I end this topic, this chapter with Assalamualaikum warahmatullahi wabarakatuh and thank you. Have a nice day.